Okay, and we're back. So this section is how derivatives affect the shape of the graph. Right? How derivatives affect the shape of the graph. We talked about what the single derivative is, right? We talked about we link together the single derivative with the slope of the original line, right? The sign of the derivative tells you whether the slope is positive or negative, whether the original function is increasing or decreasing. So we talked about increasing and decreasing relating directly to the derivative, right? Okay, now, but then we had what's called the first derivative test. Sorry, where did it go? It was maybe back here. Yeah, the first derivative test, which is basically like an extension upon the increase decrease test, right? The increase decrease test is that number line test where we see where it's positive and negative. Increase decrease test just basically tells you where the original function is increasing and decreasing. The first derivative test tells you exactly, kind of extends on that and says, okay, well, if I know it's increasing and decreasing at these parts, then I know that it is a minimum value or maximum value at those locations as well. And then we talked about, we did a couple problems with that. Now, that was single derivative, right? Single derivative. The whole section is how do derivatives affect the shape of the graph. So what if we now say, well, what is the second derivative going to tell us? Right? If we know the first derivative talks about the increasing, decreasing portions of the original function, what does the second derivative say? Right? What does the second derivative say? In figure 5 shows the graphs of two increasing functions on the interval a to b. Both graphs join points a to b, but they look different because they bend in different directions. What's interesting about this is if I think about the slopes here, if I think about the slope of this line and the slope of that line, I kind of bent it there. Those slopes look relatively the same, right? Those slopes look relatively the same. They're both about the same in those given locations. Now, what's different is how they bend, how they change, how the slope changes at any given moment, right? I know this one will kind of go, let me back it up there. I know this one will start out small, but then as I increase, as I go from A to B, it goes shallow to steep, right? If I take little snapshots of the slope, it goes shallow to a steeper slope as I go from A to B. Now this one goes from a steeper slope, then shallows out. So do you notice how they're bending differently? The rates of change are changing. Now, think about what we just said. We're examining here how the slope changes. We're examining how the slope changes. And again, another way to talk about slope is the derivative. So what I'm looking at here is how does the derivative change? What is the rate of change of the derivative? Well, rate of change is another way to say derivative. So what is the derivative of the derivative? That's what we're looking at here. We're looking at f double prime. F double prime will tell us how the original function bends, whether it bends upward or whether it bends downward. That's what f double prime says. If the graph of f lies above all of its tangents on an interval, then it is called what's called concave upward. Now, the definition is really weird. They say if the graph of f lies above all of its tangents, then I know that it is concave upward. That's like this. All of these little snapshots to the tangents, those are all below the graph, right? These little snapshots of each tangent line are all above the graph, right? That means this graph is what's called concave upward. This graph is called concave downward, okay? I like to say it like this, and I don't have a pen here. I like to say it like this. Concave upward, the definition is really difficult, but it's really visually easy to see. Concave upward will look like a smiley face, where concave downward will look like a frowny face. Okay? That's concave upward versus concave downward. Okay? I know it's continuous in between those values. I know it's increasing and decreasing at different rates. Yeah, it's all increasing between A and B. But how does it increase? How does it bend? Well, we have to look at the second derivative. And the second derivative is going to tell us the concavity at those places from A to B, okay? And then we have, and I'm just going to jump all the way down here, this thing called the concavity test. The concavity test. Okay? You know how we had the increase-decrease test? And it said what you do is you find the critical points, and then you run them through a number line, and you test points on either side. It's the exact same thing. Except this time you're going to do it with f double prime. You're going to find the critical points of the second derivative. You find the zeros of the second derivative. Put it on a number line and see what's happening. If f double prime is positive, if f double prime is greater than 0 for all x in the interval, then the graph is concave upward. So that means if the second derivative comes out positive, then it's concave upward. And again, we're relating this back to what we were thinking about during the first derivative test, right? The increase-decrease test. If the first derivative came out positive, that must mean that the original function was increasing. If the first derivative came out negative, that must mean the original function was decreasing. If the second derivative comes out positive, that means it's concave upward. If the second derivative comes out negative, that means it's concave downward. Okay, and this is just an example, a visual representation of the differences, concave upward versus concave downward. Notice that each concave downward is a frowny face, right? Concave downward, that's concave up, concave down. They're all frowny faces, right? And then concave upward, here, and here, those are all happy faces. Concave upward versus concave downward. Yeah. And notice that you can have two concave upwards butting up against each other, right? You can have two concave downwards butting up against each other as well. We don't see it in this example, but it can happen. Okay. What is that implying? Well, just as we had said, if you find the zeros of the first derivative, those are the possible locations of the maximum and minimum values. If you find the zeros of the second derivative, those are possible locations of changes going from concave upward to concave downward. Those are the possible changes. Okay, those possible changes, and I'm going to jump a slide here, are called inflection points. Now that I'm talking about it, I'm just going to jump straight to here, and then we'll go back and hit that example in a second. Those possibilities of changes between concave upward to concave downward are called inflection points. Inflection points. A point P on a curve is called an inflection point if it's continuous, obviously if it's continuous, and the curve changes from concave upward to concave downward or vice versa, concave downward to concave upward. Again, those are called inflection points. Inflection points are the possibilities of locations. Inflection points are, found by using the where the second derivative is equal to 0. But again, those are just the possibilities of locations that they could exist. Right? We have to do that number line test. We have to do the concavity test to figure out whether those are actually going to change from concave up to concave down or concave down to concave up. Now, what's interesting is those inflection points mean different things on different types of problems, okay? And that's what the last problem, which I'll go back to in a second, is going to refer to, okay? And this example, this graph is the exact same graph that we were talking about a second ago. Looking at that graph, okay, point B would be an inflection point because it changes from concave downward to concave upward. Okay. Point C would be an inflection point because it changes from concave upward to concave downward. Point D would still be an inflection point. Even though it is a corner point, is it changing from concave down to concave up? Yes. So it's still an inflection point, even though it's a corner point. Okay. So that's actually implying, does the derivative exist at point D? If it's a corner point? No. The derivative doesn't exist at point D. So therefore, I guess we have to make that same rule on, okay, well, the second derivative, it's going to be where the zeros of the second derivative are, or also where the second derivative may not exist, because that is a location where it's changing from concave downward to concave upward, and it's a corner point. So you got to be careful about that. However, point E there is not an inflection point. It's not an inflection point because I'm going from concave upward to concave upward. And then point P here is another inflection point. Okay. And again, these will be shown by using the concavity test, putting it on a number line and seeing where it changes. Now, this is not an example that you have to write down. I just think this is super interesting. Figure 8 shows the population graph of honeybees raised in an apiary. How does the rate of population increase change? How does the rate of population increase change over time? When is the rate highest? Over what intervals is P concave upward or concave downward? Really, what I want to look at is this. Do you see the inflection point in there? Do you see the inflection point where it's bending through almost, right? Where it's changing from concave upward to concave downward? Yeah. In terms of this example, look, I've got time along my x-axis, number of bees in thousands along my y-axis. What is happening at that moment? Well, I am increasing, right? I am increasing throughout this whole graph, but I'm increasing at a certain rate, and at some point, this location, like think about the slope. I should put it over here. Think about the slope as I track it along. Okay, the slope here, pretty shallow, steep. Here. Then I start to level off again, right? So this point in here is the highest possible slope, right? That's the steepest that tangent line is going to get, right? It levels out to the left of it and to the right of it. This point in there is the steepest that slope is going to get, which means if I think about the derivative of that thing, and I say the derivative is the slope, this is the maximum slope, right? So if I generally graph this, that's f prime. If this is f, that point in there is the inflection point. So what am I saying here? And this is a very important statement. If you're looking for inflection points, there's a couple places that you can look. You can look at where it bends, where it goes from concave downward to concave upward or vice versa, or it relates directly to the maximum value or minimum value of the derivative. It relates directly to the maximum or minimum value of the derivative, which makes even more sense because how can you find those inflection points? I talked about finding the zeros of the second derivative, right? The zeros of the second derivative, which means that I'm finding the maximum or minimum values of the first derivative, right? That's how we found the maximum or minimum points here, right? We looked at the zeros of the first derivative. That's where it was topping or bottoming out. So you got to understand that these things are all going to kind of chain together, right? These locations are very, very important. An inflection point here is a maximum or minimum point here, which is the zero on the second derivative, right? A maximum or minimum point on the original will be a zero on the first derivative. Zeros, inflection points, maximum, minimum values, they all go hand in hand, okay? Now, what's really interesting, and I was kind of geeking out over during the pandemic about this type of thing, is that, so many charts and graphs were being shown on a day-to-day basis, and we were always seeing this graph, like this type of graph. We were always being a lot of times we were being shown this graph, right? We were saying, oh, we hope the cases are going to be topping out at some given time, right? We hope that the cases will start to come back down again. And what we were looking at how many new cases we were getting per day, right? Or per week or whatever it may have been, right? We were saying, okay, well, we've got this many on this day, this many on this day, this many on this day. And if you track that line and you hope it's going to be a bell-shaped curve, well, then you can see, well, when is it going to top out? But what were we actually tracking? We were tracking the amount of new cases per day, which means we were tracking the rate of change in the cases, right? If I think about how much it's changing per day, I'm thinking about how we are tracking the amount, the rate of change. So we are really graphing the rate of change. So really, this is what we should have been looking at. This. And how do we find that location, right? There was a lot of time spent on how do you find that point? What is that point? Because if you can define when this point is going to occur, you can define when it's going to start to trend back down again, right? And that's what the statisticians were all trying to figure out. At what point are the cases going to come back down? Everybody wanted to know that, right? But we couldn't really tell when that was going to happen because we didn't really start seeing it level off yet, right? That's the point. That's the critical point where it's going to come back down again. It was funny. I had my TI-83 calculator, because you can actually calculate that point. You can do list 1, list 2, just like we do linear and quadratic regressions. You can put those values into your calculator, and you can actually calculate that point in your calculator, right? Given data values. And so each day I was inputting new information, trying to figure out when that point would happen. Yeah, I was a major geek. Yeah. Okay, let's take a look at this problem here. Sketch a possible graph of a function f that satisfies the following conditions. There's a couple problems like this on your homework, so I wanted to do it for you. Sketch a possible graph of a function that satisfies the following conditions. Okay, so let's analyze the graph as we go, right? Or analyze what this is telling us as we go. Again, there's a couple problems like this in your homework. You just kind of have to do a little translating, figure out what each piece is telling you, like put it into English, and then graph it from there. Okay, so what is this first bullet point telling us? Well, the derivative is positive, right? And I want to graph f, right? My goal is to graph f. The derivative is positive. The derivative is greater than 0 on an interval from -infinity to 1. The derivative is negative on the interval 1 to infinity. Okay, what is this piece telling me in here? If the derivative is positive, what's that telling me about the original? The original function is increasing. I know that this function is increasing on an interval from -infinity to 1. It's going up from -infinity to 1. It is also going to be negative. The derivative is going to be negative, so it's going to decrease on the interval 1 to infinity. Okay, let me ask you, what does that tell me? That tells me one other additional thing. It implies one other additional thing. What does that tell me? Maximum. Yeah, there's a maximum at 1, right? There's a topping out point at 1. So we know that there is a maximum at 1. Do I know what the y value is? Right? Again, we don't know what the maximum value actually equals, but we know it occurs at, maybe I should say this. Maybe it occurs at x equals 1. That's a little bit better way to say it. Because I don't know the y value. I just know where it occurs. It occurs at 1. I don't know how high or low it actually goes. Okay, the second bullet point. I believe we've exhausted that first bullet point. The second bullet point says, okay, f double prime is positive on an interval from -infinity to -2, and from 2 to infinity. Okay, if the double prime is positive, that's concave upward, right? It is concave up from -infinity to -2, and as well from 2 to infinity. So I know I've got smiley faces from -infinity to -2, and from 2 to infinity. I also know f double prime is less than 0, so it's concave down on the interval in between from -2 to +2. Ooh, I almost wrote infinity. That's a 2 there. Okay, what does that imply? Inflection points, right? There are going to be 2 inflection points. It goes from concave upward to concave downward at -2. So there's inflection points at x equals -2 and also at x equals 2, right? Because it goes from concave downward at 2, starting at concave, and then transferring to concave upward on the right of 2. Okay, I believe I've exhausted the second bullet point now. Now, bullet point number 3. Now that's a throwback here. This is a throwback. The limit as x goes to -infinity is -2. The limit as x goes to +infinity is 0. Ooh. What's this telling me here? The limit as x goes to -infinity is -2. Somebody tell me, what is that? What's this little piece telling me? The limit as x goes to -infinity. On the left side, right? On the left side, what's happening? It's leveling off at -2. Yeah, horizontal asymptote, right? There is a horizontal asymptote on the left side. Horizontal asymptote, how do I want to put this? On the left side, that's just my notation here, at y equals -2. I know it's going to level off on the left side at -2. I know it's going to level off on the right side at 0. So now we've kind of translated all this from math to English. Now let's, or somewhat English. And so now let's actually graph these parameters. All right, let's see what's going on. Okay, some really important things. I don't know any y values, right? Well, I guess I do know 2 y values, -2 and 0. I know this is boundary. It's got some boundary lines at -2 and 0. So what I'm going to do here is I'm going to say this. Here's my 0, obviously, -1, -2. Because on the left side, I've got a horizontal asymptote, right? On the left side, it's going to level off to something. On the right side, it's going to level off to my axis. So I know it's kind of like underneath here. Now, I know it's going to increase from -infinity to 1, and there's this maximum value at 1. So I know there's an interesting point happening here at 1. I know that there is concave downward. There's inflection points at -2 and then +2, right? So there's something interesting happening at -2, something interesting happening at +2. There's inflection points, and then there's this maximum value happening at 1. Okay, so I know, I guess if I want to go from left to right, I know it's going to like level off over here. And then it's going to go from concave upward, which that's a smiley face, right? I'm glad I drew that correctly. That's a smiley face. To concave downward. At -2. Just kind of put it somewhere in the middle there. Then is anything happening at -1? No, I think I just put that in there for reference. Nothing's happening at -1. But then at +1, it's going to max out. It's going to go the highest it possibly can go at 1. Now, I'm thinking this. Because I need to make it go concave downward between -2 and +2. I think it needs to crest over the top of my dotted line. I think I need to go up over here. top out here at 1, then inflect back down again to level out here. Yeah. Because if I topped out underneath that asymptote, I wouldn't be able to come back up again because there's no minimum value. We're not told that there's any minimum value. Okay. So there are inflection points here and here where it changes from concave upward to concave downward to concave downward to concave upward, right? And it's a slight happy face, right? I did draw it as a happy face, just like a really, like melted happy face. Right? So it's still concave upward from 2 to infinity. I would go back through and just double check. Okay, did I meet all my parameters? First thing, is this increasing from negative infinity to 1? Is it going upward until I get to 1? And then it goes back downward again? Yeah. Is it decreasing from 1 to infinity? Yeah, it goes downward from 1 on. Is there a maximum point at 1? Yeah. Is it concave upward from negative infinity to negative 2? Yep, there's a happy face there. It's a slight one, but there is a happy face. Is it a frowny face going from negative 2 to 2? Yep, big one. Kind of slumped on the left side of it, but whatever. On the right side, 2 to infinity. Is it concave upward again? Yep, happy face. Are there inflection points? Is it changing at negative 2 and positive 2? Yep. Do I see a horizontal asymptote at negative 2 on the left side? Yep. Horizontal asymptote at y equals 0 on the right side? Yep. Questions about that? Good there? Okay. Okay, last thing we're going to talk about, last new thing for the notes here. It's what's called the second derivative test. The second derivative test. Now, the first derivative test and the second derivative test tell you the exact same things. Okay? The first derivative test and the second derivative test have the same conclusions. Okay? They both tell you where there are maximum and minimum points. So when do you use the first derivative test as opposed to the second derivative test? I mean, it's kind of like just a question by question basis. There are actually problems in your homework assignment that tell you to use both and then analyze which one was more difficult. They both tell you where the maximum and minimum points are in the original function. Now, how do you know based on the second derivative? Well, you look at the zeros of the first derivative. Okay, you look at the zeros of the first derivative. So you're looking at the critical points, right? You look at the critical points of where the first derivative is equal to 0. Find those critical points. Then you take those critical points and run them through the second derivative. You take those critical points and then run them through the second derivative. If the second derivative comes out positive, then it's a local minimum, which makes sense because if the second derivative is positive, isn't that another way to say it's a happy face? It's concave upward. The second derivative is positive, so therefore it's a happy face, which means that therefore at that point it's got to be a minimum point, right? It's a happy face. If it's a frowny face, if f double prime is negative, if the second derivative is negative, okay, that's a happy face. If the second derivative is negative, that must mean it would be concave downward, right? Concave downward, so meaning it's a topping out point. So maximums and minimums can be used, or you can use the second derivative to figure out whether it's going to be a maximum or minimum point. Just run it through. You'll get a value. And again, you don't care about the value, you care about the sign of that value. If it comes out positive, then it's a local minimum. If it comes out negative, then it's a local maximum. Now, what's interesting to point out here is that, for the first derivative test, you're kind of doing the same thing, right? Aren't you really finding the critical points and then putting them on a number line and seeing what's happening in between? Yeah. The second derivative test says, okay, find those same critical points, but just plug them into the second derivative. So when is it going to be easier to use the second derivative test rather than the first derivative test? Well, when the second derivative test is really easy to find, like when it's polynomial, a second derivative you could do in seconds, right? Drop it down, multiply, all that fun stuff. Bring it in front, multiply, drop the power down. Done, right? Second derivative is super easy. So then you can just run those critical points through the second derivative, find whether they're maximums or minimums at that point. It's easier to use the first derivative test when the second derivative is harder to find. If you got a rational function, ain't no way I'm using the second derivative test. I don't want to find the second derivative of a rational function. No, thank you. It's probably hard enough to find the first derivative. So therefore, it'd be easier to just use that number line test, the first derivative test. Okay. I took 2 problems out of the homework and I put them into our notes. So I'm going to do one of them with the remaining time, with the 10 minutes left that I have. Okay. This was problem 37. I took this out of the homework. Find the intervals of increase or decrease, find the local maximum and minimum values, find the intervals of concavity and the inflection points, and then use that information to sketch the graph. I have to forewarn you here, this will be, like a problem like this will be, I'll have just one of these on a test on a given day, but this will be like an entire page for you. Like, I'll just put this at the top, and you just show all your work and graph it throughout the rest of the page, because this requires a lot of work. Okay. And the more difficult the type of equation, the more difficult, the longer the work becomes. Like this is polynomial. It's one of the easier types. If I give you like a rational or a logarithmic function, well, then it gets a little bit more difficult. Or a trigonometric one, yeah, then it gets a little bit more difficult. But these polynomial ones are probably the easiest types. Okay, let me stop talking, just do it. Find the intervals of increase and decrease. Okay, I have to do the ID test, right? Intervals of increase and decrease. Okay, that means I've got to find the critical points. So the critical points are where the derivative is equal to 0. So let's find the derivative. 3x squared minus 12. Super easy derivative, right? 3x squared minus 12. So my critical points, now, does this not exist ever? No, this is always going to exist, right? This isn't rational. This isn't square root, anything weird, logarithmic. So let's just figure out where the zeros are. 3x squared minus 12 equals 0. So 3x squared equals 12. So x squared equals 4. So x is equal to plus or minus 2. People tend to miss critical points when you forget about the plus or minus of a square root. Don't let that be you. Always remember the plus or minus on a square root. You might be missing a critical point if you forget a plus or minus. All right, so ID test says we got to put this on a number line. And so I have to examine -2 and +2 and figure out some test points in between. So maybe let's pick -3, 0, and 3. Now for the ID test, I run those points through where? The derivative, not the original, but the derivative. Right? Because I need to figure out what's the slope at -3. Is it positive or negative? What's the slope at 0? Is it positive or negative? What's the slope? And to find the slope, I just run it through the derivative. So the derivative at -3, so that'd be 3 times -3 squared minus 12, which gets me a positive number. I'm just going to write a plus sign for a positive number. I don't care about the fact that it was 15. I care about the fact that it's positive 15. If I plug in 0 here, that's going to give me a -12. So it gives me a negative value. If I plug in 3, okay, that would be 3 times 9, which is 27. 27 minus 12 is, again, that 15, which makes sense. It was squared. So, yeah, this is symmetric here. It's going to give me a positive 15 again. So this goes from positive to negative to positive. So if I want to answer, find the intervals of increase or decrease. Oh, let's go back to red. Here's the answers for part A. Increase and decrease. Well, this is going to increase on the interval -∞ to -2, and also from 2 to infinity.
Did you get that Ukrainian quiz done last period or not?
Oh, shoot, I completely.
Okay, that's right. I'll get it next period.
Sorry. And then it decreases from -2. Oops, I wrote 2 negatives. -2 to +2. So that's part A. Find the intervals of increase and decrease. Find the local maximum or minimum values. Okay, now I could run the second derivative test. I could, but I'm already here, right? I've already run the ID test. So I can see the first derivative test, right? The first derivative test, if it goes from plus to minus, increase to decrease, that's a maximum. If it goes from negative to positive, from decrease to increase, that's a minimum, right? So first derivative test that says that the -2, there is a local increase to decrease maximum at, and I'm going to say -2 comma something. I'll figure out what the y value is in a second. And then there's a local minimum because it's going from decrease to increase at 2 comma something, right? Let's figure out what those y values are really quick. And to do that, we just run them through the original. So we've got -2 to the third. That's not squared, that's the third. Minus 12 times -2 plus 2, which gets me an 18. -2 comma 18. Can we still say that 18 over there? Oh, yes. And then we run +2. 2 cubed minus 12 times 2 plus 2, which gets me -14. The reason why I'm finding those y values is because part E says to graph. Okay, part C says find the intervals of concavity. Now, for that, I need to find the zeros of the second derivative, right? So f double prime is going to be just 6x, isn't it? Really very, very simple second derivative. You want to see the second derivative test in action real quick? As a side note, what is f of -2? -12, right? That means it's concave downward at -2, which means it's got to be a maximum at -2. What's at +2? +12, right? Which means if it's positive, it's got to be concave upward, which means there's got to be a minimum point down there. Local minimum at +2. That's what the second derivative test does. Okay. However, I digress. I go back. So the zeros of the second derivative are where the possible inflection points are, right? So now I just do the concavity test. Here's 0. I pick something to the left, to the right. Now, we kind of just did that. If I pick anything to the left of 0, say -1, isn't this going to come out negative? 6 times -1 is -6. Anything to the right of 0, say 1. 6 times 1 is +6. So therefore, I can say that this is, I abbreviate concave downward as CD and concave upward as CU. So if you see that in my notes or in the homework keys or anything, that's what that means. Concave downward from -infinity, to 0, and concave upward from 0 to infinity, which means it changes at 0. There's an inflection at 0 comma something. And since that original function had a y-intercept of 2, it was 0 comma 2. And I've run out of time to graph. Sorry. I'll graph that as we start on Tuesday and then you have the rest of the day to work. Sorry. Thought I was going to get it done at 10.